Second member seminar of this semester. And so today we'll have a talk by Xin Liang from the Computational Mathematics Group about structure and computation, algebraic Riccati equations as an example. Let's please welcome our speaker.
Okay, thank you for the introduction, and thank you for the organizers to give me a chance to show my recent work and also my area here, and also thank the organizer to reshape the talk. They provide invaluable comments on the shape of the slides. Okay, so today I will talk about something about algebraic Riccati equations. Okay, so first, it lies in the area of numerical analysis and scientific computing. Maybe the pure mathematicians think this area is not interesting. Let me take several big figures words to show you are wrong. So the first one is John von Neumann. Everyone knows him. He said the truth of a theory is less stable than a computation because once the computation is made out, it is fixed, but the story may be renewed. So the next is the Wolfram, a friend of physician, right? He is a builder of the mathematical software. He said all processes can be viewed as computations. Again, the Richard Hamming, an expert, a famous expert in computer science. He said the purpose of computing is insight, not numbers. You think computing is not interesting because you think it just want to get numbers, but it's not the truth. Okay, so the Wilson, the 1982 Nobel Prize winner in physics, he said in past 2 decades, scientific computing has become the third pillar of science alongside the theory and the experiment. Actually, you do experiment in computers. Okay, the final one is the Nick Trapson in our area. He said since the latter part of the 20th century, most of applied mathematics has become numerical analysis. You just compute in a computer. Okay, so I would say computation. The computation is everywhere. The first example is the weather broadcast. This is the picture of a typhoon. We modeled the atmosphere movement by Navier-Stokes equation, and then use supercomputer to solve the Navier-Stokes equation. Then you can make the weather broadcast, especially typhoon or some extreme weathers. The second one is a missile carrying a nuclear weapon. The picture is taken from Wikipedia. There's a lot of process here. For example, the dynamics of the missile and the combustion of the okay, and also the explosion of the nuclear materials. And the third one is a vehicle design. This is a plane there is interaction with the air around it. Also, we can design cars, trucks, a lot of things. This term is medical imaging. You can you go to the hospital and take a ultrasound test. Then, with the help of radon transformation, the doctors can see what is happening in your body, inside your body, without break your body. Okay. Here is the 2 babies. Okay. And also, at least everybody use computations when you buy tomatoes, cucumbers, right? Okay, so my major is a little field in scientific computing named numerical linear algebra, which is also known as matrix computation. Nearly each practical task to be solved ultimately leads to a problem in my area, namely problem in matrix computation. For example, we have a phenomenon here. It is a classical model in classical mechanics or mechanical engineering. This is three spring oscillators linked by four strength spring from the ceiling to the floor. Now it is static. It is static system. You have suppose the x represent the position or the displacement of the oscillators. Then you have to solve the linear equation ax equals b to find where the three oscillators are. So the static word is not interesting. So we cut the last springs. Then we get dynamic systems. It is also easy. The derivative of the x equals is proportional to x. Then you have to solve this. The solution is something like this. You have to solve the eigenvalue problems. Ax equals lambda x, or maybe you should compute the exponential of a matrix. Still, it is not very interesting because the system do it automatically. So where is the human? This one. We put a damper here. We say it is a control. Here is a U. For example, there is a hand to pull the damper in order to make the difference make the difference of the system. Then the solution is something like this. Also not interesting. We know we cannot find some guard to stand here and do the control every time. So we hope to make a feedback control. Means the damper works proportionally to the state. So here we have the solution. Fall back to the case of this one. It is a autonomous system. Again, we solve the eigenvalue problems. Finally, we know put someone here or some machine here, you have to pay cost or energy. We try to minimize this energy all the time. Then after some calculations, you have this matrix equation to solve. This is the so-called algebraic Riccati equations. Once you solve this matrix equation x, you solve the x of the solution of this equation, then you can compute this minimal feedback f as this term. Okay, so how to compute? Again, someone say, this is the word from William Kahan. He is the designer of the float point number standard for the computers. Also the standard of the computer how to compute real numbers of addition, subtraction, multiplication. It is the work of Kahan. He said a computer can deliver a wrong answer with a speed you cannot match, and also a correct answer with a slowness you cannot tolerate. So we have to do it very carefully. At least we can make a small example like this. Consider we try to solve linear equations ax equals b. Everybody, once you learn the linear algebra, you know the solution. Is we have an analytic expression x, the s element of x equals the ratio of two determinants. So if you try to use this formula to get x, you have to compute n plus 1 determinants. Each determinant you have to is consistent of n products. N factorial products. Each product is a product of n numbers. So totally, the process requires this term of operations. It is of the order exponential. So we cannot suffer this. Also, we cannot tolerate. The computer cannot compute the solution in this form. even the computer works very fast. So the right way is Gaussian elimination. Everybody should know this. This process involves 2 over 3 n cubic operations. And this process has been known by the ancient Chinese mathematician 20 years ago, although it is named after Gauss. This is a picture of the book that is related to this Gaussian elimination. Okay, someone may know the Strassens algorithms, which is developed in 1969, not too far from here, from now. It is smarter with some constant times n to the 2.8 its power operations. But actually, the modern computers don't use this smart method because it is not as fast and stable as expected. Okay, so indeed, so how to design the algorithms? We say any algorithm has to be proposed very carefully, considering efficiency, accuracy, and stability. We have a belief that the better the mathematical property of the problem is, then the better of the numerical properties of the algorithm is. For example, we try to inverse this matrix, this n-order matrix A. If it has a structure, diagonal structure, namely the matrix is a diagonal matrix, then you can invert it in n operations. And if the matrix is upper triangular, you have to use 1/3 of n cubic to invert it. But for the generic matrix, you can just pay 6 times of this one to get it out. So we say new structure brings new property. This diagonal has the richest structure. So the algorithm works the fastest, right? So once you're working on any problem, try to solve it on computers, you should look for any special structures and then apply it in your algorithms. I will show the examples on algebraic Riccati equations. So let's first talk about the name of algebraic Riccati equations. This is a virtual dialog. I designed it. So the Jacob Bernoulli says want to solve these differential equations. The derivative of y equals p plus qy plus ry squared. And Riccati said he can solve it for some special forms of this equation. Then Daniel Bernoulli and Leonard Euler said, why not call it Riccati equations to remember Riccati? But the story is not so happy. The famous Liouville said there is no elementary method to solve the generic form of this equation. So we have to compute it out by computers. Okay, so let's talk the true history of the algebraic Riccati equations, which comes out in 1960s in the area of modern control theory. These 5 persons are the big figure in control theory. This is Wiener. His name is used to name the Wiener process. This guy is Lev Pontryagin. He has a Pontryagin maximal principle. This is Richard Bellman. We have Bellman equation. This is Rudolf Kalman. We have Kalman filter. You may have heard this name, right? Because we have the Yao filter. Okay, this guy is Qian Xuesen. Every Chinese know him. He is a Chinese hero who developed the missile for China, and also the pioneer of the control theory. Okay, let's come back to our topic. This is the fundamental problem in modern control theory. Nearly the same with the previous equations I showed before, except that we have several stochastic process involved here. Okay, so WI is a stochastic process. We say it is they are independent standard noise. Detailed, they are a Wiener process or Brownian motion. Here, x the red x is the state variable. Then the blue u is the control, or we say input, and this term is the cost weight, or say energy weight. It is a positive definite matrix. And this F is the feedback. We try to minimize the expectation of the total energy with respect to the feedback. So one thing to be mentioned is the time is infinity. In practical issues, maybe you hope to minimize the total energy in a period t, limited time t. But the limited time t derives to differential Riccati equations. It is still very difficult to solve even today. So I only talk about algebraic Riccati equations. Okay, using some calculus of variations, finally you will lead to this stochastic continuous time algebraic Riccati equations. Has a very complicated form, but you can see it is a matrix equation, and the degree is basically 2. Once you solve the solution x, you can get the minimal feedback f in terms of this one. Okay, but it is still difficult to solve, especially in 1960s. The computer is very poor compared with the modern computers. Although it is very fast in those days. So the big figures want to solve the problem. So they say, why not drop the randomness, because they should be very small. So we throw the the stochastic process away and use the calculus of the variations. We have the continuous ARE in a very simple form like this. It is a quadratic matrix equations. It is also a system of quadratic equations. Maybe our algebraic geometry guys very familiar with this term. So you can help us to get some information for this. At least we know the equation should have infinitely many solutions, and the set of the solutions should be manifold. But in the control theory, we only need to compute the unique minimal positive semi-definite stabilizing solution. The meaning is the solution should be positive semi-definite, and in all positive semi-definite solutions, it should be the minimal one, and also it is a solution which stabilizes the whole system. It is a concept related to the control theory, so I don't want to show it here. So let's see the structures to coincide with my title. So we have the CARE, quadratic matrix equation. After easy calculations or observations, you can see this. You can reformulate the equations to this one. You see here the first line is A minus B transpose X equals A minus B transpose X. And for the second line, the minus C transpose C minus A transpose X equals XA minus X B transpose X, which is exactly this term. So there's nothing special. The special thing is this matrix is a Hamiltonian matrix. The Hamiltonian matrix is a self-adjoint representation with respect to the symplectic metric of the space. So for the Hamiltonian matrix, the 2m by 2m matrix has n eigenvalues located in the left half complex plane, and another n, the other n eigenvalues located in the right half plane. This is just an eigenvalue problem because this is a matrix. This is the basis of the invariant subspace, and this term is a representation of this linear transformation performing on this invariant subspace. So which subspace? We know here is a 2n by 2n matrix. We have 2n eigenvalues, but only this term is n by n, so you have to compute n by n special eigenvalues. So which eigenvalues should be computed out? The solution of this X should satisfy that the eigenvalues of this term has a negative real part. Also, the eigenvalues should be located in the left half plane. Right, just the left part. Okay, this is one structure. Another structure is this one. Because we know the wanted eigenvalues located in the left half plane and the unwanted eigenvalues located in the right half plane. So we can use a Cayley transform or named by Möbius transform. We can transform the left half plane to a disk in the complex plane. Then use this idea, we can transform this continuous time ARE to this direct discrete time ARE. You see here is a parameter gamma involved here. This gamma controls the transformed disk, the size of the disk. The structure is not new. The first eigenvalue structure, this Hamiltonian structure is found by Richard Bellman. And this one is found by Anderson. They all found in 1960s. But how to use it to compute the X? So we consider a special case. Here A is n by n, B is n by m, C is L by n, where with the m and L much less than n. Because m is the number of the input, or say the number of control, and n is the number of the state of the system. So we hope to use a few inputs to control a very huge system. For example, we can use 4 parameters to control a whole plane, which is flying in the air. Another setting is A is sparse. Usually it always holds because the system the part of systems only related with its neighbors, so it is sparse. So there are at least 4 classes of methods: projection methods, alternating direction iteration, Newton's method, Cayley subspace iteration. You see the work recently in the 20 years, in only 20 years. Between 1960s and the beginning of this century, there are a lot of methods designed for the small scale method, namely this n is small, but we assume n is very large. So this is our work. We design a method called flexible fixed point iteration, which is equivalent to a method, an old method named RADI here, this work, and equipped with a new strategy on the parameter gamma. So we use a different way to derive our method, but it coincides with the old method. So how to design this? We discover some new structure here to have this. Okay, you see, so the method is old. So what is new? It's only a new strategy on gamma. Is it useful? Also, available to be published? Also, let's see it. There are experiments on the benchmark problems. The first one is comes from Siemens, modeling a steel profile cooling for the high-speed train. The state of the art use 8 seconds to compute it out, and our method is 6 seconds. We get a 1.3 speed up. And another example, modeling the temperature and water vapor transport in the human lung. We get 2.3 speed up. So it is useful. So as time flies, we know the computers has strong power. The power is dramatically increased. So why not solve the stochastic CARE directly? Yes, everybody think like this. So from the beginning of this century, we have the methods to solve the SCRE directly, like Newton's method, Lyapunov-Stein iteration, and the homotopy method. But they all rely on the differentiability to solve the system of the quadratic equations. It is strange. So I think the key is the lack of the clear algebraic structures. Can we find some out? Yes. We use the left semi-tensor product to deal with the stochastic CAREs as easily as the simple ones. The semi-tensor product is defined is also very easy. If the matrix A and B has an inapt size to be multiplied, then we can copy A several times and copy B several times to get their size compatible to be multiplied. You can examine this product satisfies all the arithmetic laws of the classical matrix product. With the help of this product, we can transform this SCRE to this form. You'll see the form coincides with the previous DARE exactly, except that the product is replaced by this semi-tensor product. So nothing special. Under this clear structure, we can design our flexible fixed point iteration. And here is an experiment. Also, the real example from Siemens. The state of the art solve a problem involving only one random process with the number of the non-zeros in the stochastic part only 1% of the whole system. They solved this problem in 2,000 seconds. But by our method, we solve it. We solve the problem involving 4 stochastic process and a larger, less sparse stochastic coefficients. We solve it in only 100 seconds. To compare with the state-of-the-art methods, we compute a small example with only one randomized stochastic process. We only solve it in 10 seconds. So we get 220 speed up. You'll see the structure is very useful in the computation. Again, so we can use our method, our idea to solve other algebraic Riccati equations like M matrix ARE, which appears in Markov motivated fluid cube models, transportation equations of particles, non-symmetric AREs like Nash games and Stackelberg games. Also, beta salpeter eigenvalue problems arising in electric structure calculations. A lot of applications. Our approach is very easy to be generalized for these problems. So here is a very small example for the transport theory. The state-of-the-art method used 2.8 seconds, but our methods only 0.1 seconds. We get a 25 speed up. So you'll see the structure is very important in the computation. and the computation benefits from the mathematical structure once you reviewed it. Okay, that's all. Thank you for your attention.
Thank you very much. Any questions? So you mentioned a list at the previous slide, some examples of other equations.
Okay.
So should I think of it that for each equation you could have a theorem? This can be solved in the following process, or is there one overall?
Yeah,
result?
we have an overall theorem. I mean, theorem built for all the kinds of different types of AREs.
So does it really work for all algebraic Riccati equations, or
not all? Have some limitations.
Right.
Yeah,
okay.
yeah.
But for each of them, you have a kind of a clear, concrete result.
Yeah.
That's how I should see it. Okay, thank you. And let's say if I kind of push the boundary, and what about functional equations for matrices? So kind of go back to differential equations or functional equations for matrices, depending on the parameter.
I mean, it is different areas in the computational mathematics. It is very difficult. As I said, the differential Riccati equations is difficult to solve even today. You have to make a discretization of the time and have a very small step size to let the system evolve along as the time goes. Yeah.
Okay.
And in each step size, you have to solve an algebraic Riccati equations. Yeah.
Any more questions, comments? No? Okay, let's thank our speaker again.